Hello all, this is Shatabdi Acharya from Vedang Institute of Technology. In the previous video, we were discussing about the general introduction about haloalkanes and their chemical methods by which we can prepare them. So, continuing that lecture further, in this video, we will be dealing up with the physical as well as the chemical properties of alkyl halides. So, to start off with, let us take the physical properties first. So, the first physical property we need to take is physical state or the state of existence of haloalkanes and their smell. So, haloalkanes, in case of haloalkanes, the lower members are mostly gaseous at room temperature. The higher or the other haloalkanes with carbon 18 are colorless sweet smelling liquids and higher members are colorless solids. Okay. So, lower members are gaseous, up to C18 they are liquid and beyond that they are solids. Now, if I take up boiling point, then the order of boiling point stands out to be Rf has the smallest, like the least boiling point, then Rcl, then Rbr and Ri. Now, why so? Boiling point is related to the size or the van der Waals interaction. So, as we go on increasing, first thing you need to keep in mind is keeping this alkyl group same. If I am increasing the size of the halide group only, okay. So, what happens when the size of the halogen group increases, that increases the surface area of the compound, and as a result of which the van der Waals interaction between them or the London forces between them increases. As a result of which what happens, the boiling point increases. Okay, so iodine has a larger surface area and outer electrons are loosely bound. This makes iodine a highly polarizable atom, and a polarizable atom increases London force of attraction, which causes increase in the boiling point. Now, boiling point increases with the size of alkyl group also. So, with the size of alkyl groups, the boiling point goes on increasing. For isomeric alkyl halide, the boiling point decreases with branching because the exposed surface area becomes lesser and lesser. If I see the solubility, then haloalkanes are polar in nature, yet they are insoluble in water but soluble in organic solvents because they are inefficient in forming hydrogen bonding with the hydrogen atoms of the water molecule, because they are not able to form hydrogen bond with water molecule. If I see the bond strength, then the bond strength obviously goes on increasing with the electronegativity of the halogen atom. So, fluorine being most negative has the highest bond strength, and when we move from chlorine, bromine and iodine, this gradually goes on decreasing. Now, if I see the densities, then the density of haloalkane increases with atomic mass of halogen and decreases with increase in size of the alkyl group. So, density basically is mass by volume. So, if mass increases, density increases. If volume increases, density decreases. So, for the same alkyl group, the density follows the order Ri greater than Rbr greater than Rcl greater than Rf. Okay, because mass is getting gradually decreased, therefore density is also decreasing. Now, for the same halogen, density follows CH3x has most density, followed by CH2x, C3H7x. Why? Because here the volume gradually goes on increasing. Volume mostly depends upon the surface area. So, surface area goes on increasing, therefore volume goes on increasing, therefore density decreases. Fluoro and chloroalkanes are lighter than water, whereas bromides and iodides are heavier than water because of their mass. Now, the important thing here to note is the dipole moment. If I see, haloalkanes are polar compounds and their polarity depends upon the electronegativity of the halogen atom. So, dipole moment of halomethanes follows the order CH3Cl greater than CH3F greater than CH3Br greater than CH3I, because electronegativity of chlorine is increasing greater than fluorine greater than Br and greater than I. So, it follows this order. Dipole moment of fluoromethane is less than chloromethane due to very small size of fluorine. Okay, so due to the size of the smaller size of fluorine, the dipole moment order in case of CH3Cl and CH3F is getting reversed. Although fluorine is more electronegative than chlorine, but it takes up the second position in the series. Now, if I see certain chemical properties, then in the previous lectures or in some lectures back, we dealt about the nucleophilic substitution, basically the SN1 and SN2 reactions. So, we will not take up the mechanisms here in detail, we will just see what are the reactions. So, if alkyl halide is getting reacted with aqueous KOH, then there is a nucleophilic substitution of OH in place of X. Here the nucleophile is OH negative. Okay. Aqueous KOH causes nucleophilic substitution. Alcoholic KOH causes elimination. You have to remember this. Then when it is reacting with AgOH or Ag2O, it is getting substituted with ROH. When it is reacting with Ag2O dry, same ether is being formed, ROR plus 2AgX. In case of KSH, it is K plus and SH minus, so simply RSH. Okay. Haloalkanes. Now, if it is getting reacted with sodium alkoxide, it will break as O minus Na plus. So, this is okay. So, this will be ROR rather than RSR. This will be ROR. If it is sodium cyanide, then it is C minus Na plus. So, sorry, the reactions are written wrong here. So, it will give you RC triple bond CR dash. Okay. If it is reacting with RCOOAg, it will give you RCOOR dash, which is an ester. With NO2, RNO2 is getting substituted. With AgNO2, it is RONO. Okay. Here it is written like the opposite reactions are written, some mistakes are there. So basically what happens with KNO2, the product will be RNO2, and with AgNO2, the product will be RONO. Okay, this is because this is mostly ionic compound. It will break off into its ions K plus and Na2 minus. But here this is a more covalent, and as a result the ions will not be getting separated. So oxygen will attack through its lone pair. In case of NH3, it will form amines. Then further substitution will take place till tertiary amine. Okay. In case of AgCN, again it is covalent, so it will be AgNC, isocyanide, and whenever it is reduced with Na and ethanol, you get RNHCH3. Okay, a secondary amine. Now, some important point to note here is groups which possesses two nucleophilic center are called as ambidentate nucleophiles. Example, cyanide and nitrite. KCN is predominantly ionic and provides cyanide ions in solution. Although both carbon and nitrogen atoms are in a position to donate electron pairs, the attack takes place mainly through the carbon atom and not nitrogen atom, since carbon-carbon bond is more stable than carbon-nitrogen bond. Therefore, when haloalkanes react with KCN, we obtain cyanide. But AgCN being more covalent, so the attack will take place to the nitrogen atom. AgCN is mainly covalent and nitrogen is free to donate its electron pair, forming isocyanide as the main product. Now, if you see certain elimination reactions, basically what happens, here elimination of a hydrogen and a halogen groups takes place. So, it is called as dehydrohalogenation process. Alkyl halide undergoes beta elimination reaction in presence of potassium hydroxide alcoholic KOH to give you alkene. Okay. So, the alpha position is that attached to the halogen group. The beta hydrogen is getting eliminated along with the halogen to give you the respective alkene. Reactivity of haloalkanes towards elimination is tertiary, which is greater than secondary, greater than primary, which is because of the plus I effect of the alkyl group. Now, in dehydrohalogenation of secondary and tertiary haloalkane, there is a possibility of formation of two isomers. Then it is governed by Saidze's rule. What Saidze's rule was saying? The elimination will take place from that carbon which has lesser number of hydrogen atoms. Basically, we will try preventing the formation of terminal alkenes. Okay. So, here if you see, there are two beta positions. One is this, one is this. Basically, we will go for this site because terminal alkenes are not that stable. See, this is getting a yield of 81%, whereas this is getting only 19%. Okay. Now, if I see the reaction with metals, when Rx reacts with Mg and dry ether, you get a reagent called as Grignard reagent RMgX. Okay. Now, carbon magnesium is highly polar covalent, whereas magnesium halogen bond is ionic. Okay, this bond is ionic and this is polar covalent. This is break off as R minus and Mg plus. Reaction with sodium is known as Wood's reaction, and this reaction is used for the preparation of even number of carbon atoms, like alkyl or alkanes containing even number of carbon atoms. So basically what happens, if I am reacting 2 moles of Rx with 2Na, then 2NaX will get removed and these 2 Rs will be joined together to give you a alkane. Okay, and reaction with lithium will lead to liberation of an LiX and substitution of lithium in the chain. Now if I see the reaction with zinc, it is called as Franklin reagent. So here what happens, C2H5 reacts with zinc to give you C2H5 whole 2 zinc plus ZnBr2. Zinc bromide is getting removed. Again it is taking place in the presence of ether and heat. Now if I see Wood's-Fittig reaction, we have seen Wood's reaction. There is another reaction called as Fittig reaction. What happens in Fittig reaction? In case of Fittig, there are 2 benzyl substituted or benzene substituted halogen. They are getting reacted or reacting with 2 sodium atoms to liberate 2 NaX, and they will result in the formation of dibenzene or diphenyl. Diphenyl will be produced in this case. This was Fittig reaction. Wood's reaction was taking place in case of alkyl groups. Now if I will combine this Wood's and Fittig, I will get Wood's-Fittig reaction. Here what will happen, NaX and this NaX will be getting removed and the R will be getting attached in the place of that X. Now this is a name reaction called as Corehouse reaction. Here Rx in the presence of LiETO3, ET3O, they will give you RLi, which when reacts with copper iodide will give you R2CuLi. This is again an organometallic reagent. When R2CuLi is reacting with Rx, another haloalkane, they will give you RR, RCu plus LiX. Okay. So these all reactions you need to remember. This was all about the chemical properties of haloalkanes. This brings us to the end of this video and even the end of this chapter. In the next class, we will take up haloarenes. I hope you are you're clear with the reaction shown by alkanes. We will meet in the next video. Till then, thank you so much for watching.